Now, uniform convergence and pointwise convergence. And for this section, I would like you to remember and focus, we'll see this at least twice in this lecture, this example, 1 minus x to the n. This consisted of these graphs that become sharper and sharper at 0. We could also do x to the n when it would just be reflected. And it converges to this discontinuous function that's 0 when x is not equal to 0 and 1 when x is equal to 0. And it converges pointwise. So you fix an x, you get this power function, 1 minus x to the n. So for fixed x, this has two options. Either it's 1 to the n, which is constant and converges to 1, or it has absolute value less than 1, and the powers converge to 0. So this is an example where continuity was not preserved. And the question is, when can you preserve continuity? And the crucial additional assumption, just like previously, I drew this also in red here to emphasize this is kind of the strengthening assumption that saves you. Previously it was compactness, now it converges uniformly. So if you have a sequence of continuous functions that converge uniformly, then the limit function is continuous. And by the way, just a small thing about notation, especially when you're doing the exam, you can write pointwise convergence with a single arrow. I would still add the word pointwise to emphasize that you're using pointwise convergence. If you use 2 or more arrows, sometimes people use 3, that means uniform convergence. Then you don't have to usually state uniform, but it's still a good practice, just so you make sure that your reader understands what you're saying. Okay, so let's prove this. And this is, remember what I said at the beginning, that there are many quantifiers that need to be chosen. There's this n and there's this x, and that's something that we'll see immediately. So we want to show that the limit function is continuous, not uniformly continuous, just continuous. It doesn't have to be uniformly continuous. That's good to keep in mind. So we have to fix a point, x, x. Previously I don't know this x naught, but now I will just denote x. And fix an epsilon. This is our setup stage. And now our task is to find a delta. I wanted to draw a picture just so we have a little bit of intuition about what we're trying to do. So we have our space x, that's some sort of a blob. We have our point x here, and that's mapped somewhere by f, which is this pink curve here. And f itself is a limit of fn's. So a uniform limit. So we know that eventually this graph fn will be close. And what we want is we have this fixed epsilon. We want to figure out a radius delta so that if we pick another point here, the function value is also close. Now, there are two things that we will use that this picture is trying to convey. One is that uniform convergence means that these graphs are close. So the distances here are small. And then continuity of this function means that these function values should be close. So by triangle inequality, these two values of the function should be close. But there are quantifiers here, and there's delta that I haven't specified how to choose. And that's kind of the hardest part of writing this. And that's why these choices are made in this blue region here, but this is done after doing the computations. So I'll write here choices. Right. So we need to make choices, but we cannot do it before we actually know what choices need to be made. So this is similar to the scheme that we've seen in this meme before. Well, we have set up our proof, but we have to think and estimate. And now the new thing that comes up in this proof is that when we make our choice of delta, well, we ask ourselves a question, how to make it small, the estimate that we get from our thinking. And we need to make many choices. In particular, in this case, we need to make 2 choices. So before we know how to write this proof, we have to actually estimate. Okay, so motivated by the picture and the general idea that if you have a sequence thing, you want to compare to the sequence. So we want to estimate fx minus fy. We will have an assumption x is close to y. But, okay, how do we estimate that? We want to bring in the sequence somehow. So what we do is we subtract the sequence. So we have a difference of f minus fn. Then we have fnx minus fny, and the difference of fn and y. Okay, we apply triangle inequality. We get 3 terms. And the question that we have to, once you have this estimate, it might not be good enough, but once we have it, our task is now to say, how do I make all these small? Now, different terms will require different choices to make them small, and we are hoping that we can make those choices in an order that will guarantee that everything is small simultaneously. So there's a choice of delta that we still have not made, and there's a choice of n. And the order matters of these choices. If you write them in the wrong order, basically all your proof will be nonsensical and will not make sense to anybody except perhaps yourself. And the question is, what do we fix first? Well, to do that, we should look at these terms. So this is difference f minus fn, and this is difference in fn minus fn. So, well, just intuitively, how do we make each of these small? Well, this one is made small. This is small for large n. Because why is it small? Well, by convergence to that. This is also small for some large n. But already here, one thing to emphasize is these are 2 different points, x and y. So what we need here is actually these are uniformly small, independent of the point. This is where we're using uniform convergence. Okay, well, if we have chosen such an n, this middle term, how can we make it small? Well, fn is continuous. So if y is close to x, then that middle term is small. So these are small if n is big, but this is small depending on n. We have to make a choice depending on n. So because the second choice depends on the choice of n, the delta that you get here will depend on the function. We have to choose the n first. And that's usually the order to do, so that's also a good practice. But in general, but sometimes different. But choose n. Well, how do we choose it? So since fn converges uniformly to f, and we want to make these terms less than epsilon over 3, so let's, for epsilon over 3, there exists some capital N such that for all n bigger than or equal to capital N, and for all x in the set, f and x minus fx, my set was x, not k, doesn't need to be compact, we get that the difference in the function values is less than epsilon over 3. And it's better here to use a z to emphasize that it's true for all points, not just z, not just x, but any other, also y simultaneously. So we get to estimate the first and the third term. We're done. Now, how do we choose delta based on this n? Well, f capital N is continuous at x, so there exists a delta posited so that for if distance between x and y is less than or equal to delta, then fn x minus fn y is less than or equal to epsilon. Okay, so the choices that we make are actually done here. So I won't repeat them as to save a little space. So we choose n we choose a delta. And now what we have to show is that the estimate works. So conclude with the estimates that all is fine. So now we have chosen an n, we've chosen an epsilon. Let's show that all works. So with if distance x to y is less than delta and n is as chosen, then, okay, we have our previous estimate that we found from above by these three quantities. Well, the first term is less than epsilon over b by uniform convergence and choice of n. The second term is less than epsilon over 3 by choice of delta. And the third one is again the same as the first. And what we get is that the whole thing is less than epsilon. And we're done. Because if the points are close, then this left-hand side is less than or equal to epsilon. So you'll notice one thing here is that this n is only temporarily needed for this estimate. It kind of doesn't show up in the, it affects the choice of delta, but it doesn't show up and they're in too strongly here. Any questions? This is an important proof, so please do ask questions if you have anything. I'll turn the lights on. Well, you think? Okay, so first n, then delta. Often people write these in the wrong order. Okay, so now to the thing that was asked on Monday. I will have a separate video discussing this more. I don't want to do the proof now because I want to get to it, this exchanging limits. So I stated this a little bit before. Suppose we have the space of continuous functions on a space, some x or k, it doesn't matter. Well, k, you do need usually k compact for technical reasons. You define this metric, d infinity. And while I wrote here a sketch of why it is a metric, I believe that TA has discussed it, and I have discussed something similar in one of the videos. So I won't discuss it too much. But anyway, this is a metric on this infinite dimensional function space. And what's crucial about this metric, sometimes called the metric of uniform convergence, is that a sequence of functions converges uniformly to f if and only if the distances go to 0. Okay, and this is really, it's kind of a stupid statement because it's hiding within it just that these two things are the same thing in disguise. I mean, what is uniform convergence? It means that for every epsilon positive, there exists an n such that if n is bigger than or equal to capital N, then for all x in your space, fn x minus f of x is less than or equal to epsilon. So uniformly, you're close. But what does it mean? Well, the functions converging in f in your metric space x, maybe I'll emphasize the metric here. What it means metrically is that the distances go to 0. But what does it mean for the distances to go to 0? It means that for every epsilon positive, there exists a capital N such that if n is bigger than or equal to capital N, d infinity of fn f is less than or equal to epsilon. But let's see what this means. Let's write this out. This means that supremum of x in k, or your space x, being a little bit inconsistent with this, apologies for that, is less than epsilon. But a supremum being less than epsilon, I mean, a slightly weaker condition is that for all x, this means that epsilon is an upper bound. So another way of stating this inequality is that for all x in x, fn x minus f of x is less than epsilon. But lo and behold, we got exactly the statement that we had here. So these are the same statement in disguise. So this metric is really describing uniform convergence. And with that, Well, if you have a sequence of objects that converge in X in the uniform metric, then their limit converges. But you can strengthen this statement in a different way. You can say that this metric space of continuous functions, if K is compact, there's a small technicality when K is not compact, is a complete space. And I won't talk about the proof now. I'll just skip over it now. If you want, there will be a video about that later. And there's a scheme that you can look at. I will upload this notes later. It's very similar to what you were at least supposed to do on the exam. There's a setup. You start from a Cauchy sequence. You find the limit. Basically, you find the limit by a pointwise convergence argument. And then you have to prove that it actually converges to that limit. That's a little bit tricky here, but I don't want to get to it now. So this gives us a complete space to work with. And it gives us a rigorous sense of saying that somehow it's closed. It's closed under taking limits. But that closes that chapter. Uniform convergence defines as a complete metric space of functions.